range method. It's a method to find multiple roots for non-linear functions in a user-definable range. The history of root finding goes back to the early programmable calculators that HP came up with, starting with the 65, 55, 67, 25, and so on. And typically HP had a root finding application in the standard pack, usually a simple implementation. You give it a guess and it gives you a root, and an enhanced version in the math pack. In the case of the HP25, the application manuals that came with the calculator had also a root method with it. The HP34 brought in the built-in solver, thanks to the efforts of Professor Kahan. And in that solver, you gave the machine 2 guesses, and it gave you a refined guess, pushing things to the limit, the accuracy of the machine. So you didn't have to worry about saying what your tolerance was. The 41C followed the traditional path by offering a root finding application with the standard pack, and then a better version with the math pack. And of course, the Advantage ROM brought in the solver in M-code for the 41C. The 34 solver also showed up in the HP15C. And then as HP introduced newer scientific, financial, and graphing calculators, they implemented the solvers in these machines and better versions. In fact, most of the graphing calculators, you just need to give it 1 guess, and it gives you the root close to your guess. At the same time, HP began with the math pack of the HP71B, implementing the polyroot, in which you give an array of the coefficients for the polynomial, and will give you the real and complex roots for that polynomial. The method did not require any initial guess on your behalf. It figured out the guesses internally, and instead of using Newton's method or a variant of it, it used the Laguerre method. The polyroot gave me pause and thought, why don't we have something similar for general nonlinear functions? And that's what the scan range method is about. The method allows you to scan a user-definable range of values. Why? First of all, it would limit the area of your interest. Suppose you don't care about negative roots for your function because they don't mean anything to your application. So you can, focus on a positive range of values. Another case is if you're dealing with sinusoidal functions that have a large, if not infinite number of roots. Obviously, you don't want to spend your whole day just tracking endless roots. You just say, I'm interested in this range, so you have a fixed range. The search employs a user-defined steps. This defines the resolution of your search, and that's important because if your resolution is large enough, you may actually, for example, find one root, but then jump over another root that is just right next to it. So your resolution has to be right. The other extreme, if you use a very small step size, you're going to be spending a lot of time in between roots and a lot of CPU time. The scan range method locates roots that are also minima, roots that are also maxima, and then as a bonus, minima and maxima. So that actually kind of gives you a mental view of where the function is going, the highs, the lows, and the roots. How does the method do that? It detects these roots, maxima, minima, by watching the signs of the function value and the slope value. Because in the case, for example, when you have something like y equals x squared, well, you really never cross into negative territory, but you hit a root at x equals 0. So it has to watch the slope also. When that changes, it says, oh, there's something going on. Now, there are special cases where the search value may land on a root if, and that's a big if, I put it in red, the step size is small enough and it's an integer multiple of the difference between the root and your low search range. This occurs when you have integers or when the root has few decimal points. And of course you have to, if you are lucky enough to synchronize it enough that it will land on the root. This is a bonus but not a necessary way of operating. As far as the implementations, the next HP solve, is it out yet?
No.
Okay. We'll have We'll have an implementation for the 39G2. That'll be in the next HP solve newsletter. And the article has the algorithm, which I will spare you because it's a bit more complicated, the listing, and examples. The conference proceedings have similar documentation PDF files that I implemented for the 41, it should be 34, sorry, 34S, 71, the TI Inspire, Excel VBA, and even MATLAB. So you have quite a variety. I figured that would tickle somebody, at least one of them would be of interest to the audience. And then these files, I maintain them on my website. I usually keep them up to, if I add anything, so periodically visit the website to check these files. There will be, the link is in the main page. For the next slides, I'm going to do a visual representation of how the method works. I have here a small subinterval that I've kind of blown up, magnified, XA to XB. And this is the most typical way the method finds a root, is that when the function value changes sign, going, say, in this case, from positive to negative, and then crossing the x-axis somewhere in between in that range. Your choice, and you can say, okay, I'm going to use the bisection method in which your guesses are XA and XB themselves, and then you zoom in on the root, or you can say, I want to use Newton and just take the midpoint as my initial guess and then find the root. And because you know the root is in a small interval, the likelihood of convergence is very high and very fast. Now here's a case where it's the same as before, but we are landing on the root at XB. The function is changing sign, but it's crossing the x-axis at XB. And the algorithm actually tries to detect these cases first, and if not, then go in a more general case. Now here's another case where the root is also a minimum. Now notice, the function values do not change signs. It's the slope that changes sign, going from negative to positive, and the function touches the x-axis at the root, which happens to be also a minimum value. Somewhere in between. And again, you can give it either if you're using bisection. Now here, when we're zooming, we're not looking for the zero of the function, we're looking for the zero of the slope. So we can still use bisection or Newton's method or other methods, but we're seeking the zero of the slope. Here's a case where we have a minimum, but the minimum is at the upper end of this tiny subinterval at x of b. Here's the reverse situation where the root is also a maximum point. Again, the function value doesn't change signs, but the slope does, going from positive to negative, and the curve touches the x-axis somewhere in the subinterval at the root, which happens to be also a maximum. And again, you can do bisection method or whatever. Again, in this case, you're finding the zero of the slope, not the function itself. And again, here's the case where the maximum happens to be at x sub b, and you're landing on the root. Another very rare case is, which I also take into consideration, is that the root could be a saddle point. And unlike the maxima minima here, in this case, the function does change a sign, the value. But at the root, the second derivative is 0. And the method, the algorithm does check for that too. And of course, since we're observing and monitoring the slope, the changes, the signs of slope also, we are also able to find a maxima and minima. Here's one case where the minimum happens to be in the negative, the maximum happens to be in the negative territory. The function values don't change sign, but the slope does. But the function never touches the x-axis, so it's just a maximum. And likewise here, also you have a minimum in the subinterval. The function doesn't touch the x-axis. The slope values change sign, but the function values don't. And again, the implementations have methods to find the slope as being 0, but it's going to be only a minimum or maximum. There's no root in this case. But all this information gives you an impression on how the function is going up and down and when it's crossing the x-axis. Here's my first example, my beloved root testing function, exp minus 3x squared. As you can see, noted by the 3 red dots, that's where the roots are. The function has 3 roots, and then in between the first and second root, there's a maximum point, and between the second and third one, there's a minimum point. I want to scan for the roots between -1 and 4, and of course with graphics ability on calculators and computers, it really helps us just to see, to select the range. And I want my search step size to be 0.1. The tolerance value for the root is 1e to the -6, or even smaller. And then I have a function tolerance value of 1e to the -4. I use that value to determine whether the approximation for the second derivative is 0 or not. And from fiddling around with the algorithm, actually, when I use smaller values, I get in trouble. So 1e to the -4 seems to be good. Making it smaller will cause the scan range method to make the wrong judgment. I'm running on a 41C, thanks to Warren's emulator. Program's called Scan, and it starts prompting me for input. The first one asks me for the range A to B, and I enter -1, and then 4, and then press run. The next input is the step size, and it's 0.1, and I press run. And the next input is, the prompt is for the tolerance value. I enter 1e to the -6, and I press run. And then finally, the program asks me for the function tolerance value. I enter 1e to the -4, and I press run. The first input is at x equals -4.5. And when I click run, I get a very small function value, so I know it's a root. When I click run again, if I don't see any comment on that root, if it's a maximum, minimum, then I know it's only a root. Because then the program starts looking for the other point. And here, the next value is at 0.2, where the function is 1.1. And then the output following that is a comment from the program that this is a maximum point. So we know that's a maximum. When I press run again, I get the next root at 0.91, and again the program displays function. This is rounded to 5 decimals 0, and there's no other comment after that, so I know this is just a root.
What if you want more decimal places?
Oh, you can, yeah. I mean,
You run it a second time and then.
No, I mean you can. Because you're also your tolerance value will determine what kind of rounding for your roots. Yeah, displaying it doesn't use the display mode for calculations, just to show you what you want. And the next value is the minimum at x equals 2.83, where the function value is -7.08. And then the next output is the word min telling me that this is a minimum value. I click run again, and I get the last output, which is a root at 3.733. The function value is 0, and there's no comment after that except it's done because it has reached the limit that I gave. The next, second and last example is a sinusoidal function, sine x plus 1. This function has an infinite number of roots, and the function values oscillate between a maximum of 2 and a minimum of 0, which happens to be also the root. The first thing I have to do is, because the code was geared for the first test function, I need to go to label E and edit the code to implement sine x plus 1. Then I'm ready to do whatever testing I want. In this case, I want to test it in a range of 0 to 20. And I'm going to use the same step size, tolerance value, and function tolerance value as previously. After the editing and all that, I execute the scan program again, and it will ask me for the limits. I enter 0 and 20. And then for the step prompt, I enter 0.1. For the tolerance prompt, I enter 1 e to the minus 6. And then for the function tolerance, I enter 1 e to the minus 4. The first output is a maximum value at 1.52. It gives me the function value of 2, and then comments that it's a maximum. Of course, because it's a sinusoidal, we know that the next output is going to be a root, and sure thing, it will give me a root at 4.71. And it says the function is 0, and comments that it's a root slash minimum. It's a combination of a root and a minimum. And the next output is a maximum at 7.85, and the program comments that it's a maximum, followed by, of course, a root as we expect at 10.995, and it says it's a root minimum, and then followed by another maximum at 14.1, and the program again says it's a maximum. And finally, we have that combo root minimum at 17.27. And once we're that, we reach the end of the search, and the program displays that. So that's all. I hope the proceedings have the documentation, and also like if you run the 41C emulator, there's the .raw files. And like if you run a Windows HP71B emulator, you will have the emulator files. And for the TI Inspire, you have the TI files. So not only you get the documentation, but you can get stuff that you can use with emulators right away. Thank you.